I'm gonna walk you through a little bit of the platform that we've put together. It's a dynamic web application, and try to highlight some of the ways that data-driven methods have been able to provide value to this platform, what they really add to it. And then we will look over some advances that we've been able to make in capitalizing on these data-driven methods. So throughout, I'll be including screenshots from this web application. So to begin with, when an event happens, we want to produce an evaluation. And with this evaluation, we have this idea of different predictors that we're assembling. A predictor is an analysis routine, kind of an abstract idea of an analysis routine. It could be a structural analysis model or a system identification procedure, but something that we can assemble into an evaluation page to give to the owners of these structures. And this idea of a predictor we found useful to break into two categories: the conventional predictors that directly employ structural analysis calculations and things like that, and then the data-driven predictors, which are just running from the data and trying to apply some fitting and regressions to draw conclusions on the state of the structure after an event. Things to keep in mind is that building an evaluation page like this often needs to be done for several bridges at once when an earthquake is sensed at several bridges. So we need to bear in mind the computational demands that this is going to incur. And we also need to bear in mind the reader and also the developers that will be contributing to this. What kinds of methodologies do they understand? And what will make sense to the decision makers that will actually read this? Like, what subjects are they educated in, and how can they make confident decisions based on what we're presenting them? So that brings us to look closer at these two types of predictors. We have conventional modeling, which in this project we employed a high fidelity OpenSeas model. Our team member Crystal Churn and the Professor Muhammad at University of Nevada put a lot of work into developing a very high fidelity OpenSeas analysis model of the Hayward Bridge. And this has allowed us to provide very high fidelity predictors or metrics of the state of the structure. And this is also kind of a beneficial or a strong idea for a platform like this, because there's a large workforce of practicing engineers that are educated in these types of models. So capitalizing on these types of predictors allows us to kind of tap into the large workforce that already understands these methods. And then also these provide very intuitive metrics. When you have a structural analysis model that is running at from a particular earthquake, we can start reporting things like strains and displacements and drifts that are very intuitive to a lot of the decision makers that will be reading this application. But then there are also a lot of limitations for these kind of models. Engineers are very expensive, so developing these models are very expensive. And also computers are very expensive. These tend to be very computationally intensive models. And then also interpretation, although sometimes they give intuitive metrics, it also requires care. It's easy to forget that most of the theory of structural analysis has traditionally been applied in design. And so a lot of the rules of thumb that people are using are for design. And this is a very different situation than trying to actually say what the state of a structure is right now. So this can be a little bit misleading with these conventional modeling approaches. Here we see that just this model alone is 2,000 lines of tickle code and took over a year to develop, and still fine adjustments are being made, but it is largely complete. So these can be very expensive models, both on computing resources and just people to develop them. So now we want to see, how do data-driven methods compare with this? What do they offer in contrast? So this is the interface we've been able to develop for configuring state space system identification metrics. We have just a simple form, and with that, you can report on the whole history of periods that we can identify for all the events that the structure has received. This is very easy to configure, and this has allowed us to make these partial digital twins that were shown on one of the previous maps for far more bridges than we thought we would do before, because it's so easy to deploy these data-driven methods. We think this can save a lot of money on the owners of these structures, because now they know, like, at least if these methods are working for a certain type of structure, then it reduces the need to have an engineer work for, we pay the salary of an engineer for several weeks to develop a structural analysis model. All of that can go away for maybe an hour of work in configuring a system identification method that leverages data. But then how does it compare in computational efficiency? So that leads us to some of the advances that we've made in implementing this platform. To begin with, we have been working with different state space methods which just use an algebraically manipulated version of the traditional equations of motion to identify a realization of a structural analysis model. Of the analysis or algorithms that we've considered, SRAM is one was well known but generally considered to be infeasible computationally, especially when compared to traditional OKID-ARA-DC or Ho-Kalman type of algorithms. But we've actually been able to employ some parallelism or exploit parallelism that hasn't been exploited in the literature previously, so that now our implementation of this algorithm outperforms the traditional method and still brings higher accuracy, which has been a great advance in providing reliable metrics for all of these bridges, just solely based on data. And so we have been able to refine this implementation, and we're packaging it into an open source library that we're releasing under a BSD2 clause license called the MDOF package. And our colleague Crystal Churn has put a lot of time into putting a lot of different methods, exposing a lot of different methods of system ID into this package. But kind of the flagship function is one that we put together called EIG-ID that is meant to mimic a traditional EIG function that you might see in MATLAB or SciPy, where a lot of people will be familiar with passing a stiffness matrix and a mass matrix to solve a generalized eigenvalue problem that returns eigenvalues and eigenvectors. So we have implemented an API that lets you pass instead a series of inputs, a series of outputs, which is just time series data, and as we see here, it's just something that you could load from a CSV, and it can be any combination of single in, single out, multi-in, multi-out. You can pass just a single array, as we see in line 1, in the inputs, or a collection of time series arrays as the outputs, or vice versa. And this returns the same return that a traditional EIG function would give you, a set of eigenvalues and eigenvectors that we interpret as some frequencies and mode shapes for structures. This is currently available on PyPI, where packages are installed with pip. And over this week, we are rolling out documentation for the full package with several examples and everything. So that will be easy to find just from the standard Python packaging index. And then also in implementing this package, we also were able to really optimize the generation of response spectra. So we kind of separated that out into an SDOF package. We were able to lower down just simple time integration into standard ISO-C. We employed platform-independent threading, and we're able to massively improve the performance of generating response spectra. We also spent a lot of time testing different memory layouts to optimize the cache efficiency. And then we also have been able to build this for WebAssembly so it can run directly in a browser. So this package right here is a set of C routines that we've provided bindings for a Python library and also a JavaScript library that executes single degree of freedom integration about as fast as you probably can. And that leads us to conclusions. So conventional high fidelity modeling has proven to be very important. It's still indispensable in structural health monitoring, particularly for very complex structures, but it is costly. Data-driven methods drastically lower this cost, and we're already seeing what they offer precipitate into very affordable means of structural health evaluation. Also, in our packages, we've been able to leverage shared memory parallelism to drastically improve the performance of these algorithms and make them more competitive than they previously were, and by limiting global state. And these, a subset of these algorithms we're publishing for Python 3.7 and up. And that's all. Thank you for your time.